All right, thank you so much, Valentine, for the introduction, and everyone else for being here. Happy Memorial Day, if you celebrate that. So as you can see, this is a talk which, as I indicated in the abstract, concerns work in a couple of papers. One of them was joint with Akshay Venkatesh. That's what partly joint work means, I guess. So one out of two papers. And it's about the orbit method and how it can be developed in the spirit of microlocal analysis and then applied to some standard problems in analytic number theory concerning L functions. So in a bit more detail, what we'd like to do is estimate L functions on average or individually on groups like general linear groups or products of such groups, or closely related groups like classical groups, orthogonal groups, and unitary groups. We'll say a bit more about what we mean by that later in the talk. This is just kind of a brief overview of what we're getting into. Part of our task in doing so will be to understand the asymptotics of some special functions of representation theoretic origin attached to automorphic forms on such groups. So you can think of an automorphic form itself as a simple example of a special function, or for instance, a matrix coefficient integral defined in terms of an automorphic form. We'll come back to those. Much of what we're discussing is known in some form and has been for a while in the case that n is fairly small by work of many authors. So maybe the novelty will be in giving a softer approach that happens to work also in higher rank. And yeah, like I said, that'll be principally through the introduction of, well, what we're going to talk about. And yeah, we'll conclude by just kind of briefly indicating if how with some additional arguments one can attack some standard problems with these techniques. So organization-wise, we'll spend a few minutes saying what we mean by the orbit method in language suitable for our purposes. Then we'll say a bit about how one can develop microlocal analysis in the spirit of it. And then we'll go on to our applications. So I've designed this talk with an audience that is not so familiar with representation theory or perhaps with classical microlocal analysis. And I imagine that many people attending this talk will not fall into that second category, but maybe the presentation will still be useful in motivating the last couple sections. Okay, so the orbit method, our little crash course on that begins now. It concerns representations of a Lie group that we'll call G. We'll denote by frac G its Lie algebra and frac G wedge the dual of that Lie algebra. So an example to keep in mind might be the general linear group with Lie algebra, the n by n matrices, and there's a standard identification then of the dual Lie algebra also with the space of n by n matrices. So the definition that gets things started is that of a cogent orbit for such a group, which is just an orbit for the action of that group on its dual Lie algebra. That's the coadjoint representation, hence the name. So in the example I indicated with the general linear group, such an orbit would be a conjugacy class of matrices. And I guess we know from linear algebra that these are fairly rich objects to think about. Now, we spent a good semester developing their basic properties. And so a cogent orbit is a generalization of the notion of a conjugacy class of matrices. An even simpler example that I'll come back to a few times in the talk, just to give some example to draw pictures about, is when G is the special orthogonal group in three variables. So the group of rotations of three space, we can think of it that way. In that case, we can identify both the Lie algebra and the dual Lie algebra with Euclidean three space in such a way that the action of the group on these two vector spaces is given by the ordinary rotations of three space. So for this example, the orbits are precisely the spheres in R3. I've drawn some pictures of them here. You can see on the very left, I mean, maybe you can barely make it out, it's a little dot. That's the sphere consisting of just the origin. So this the singleton sphere. And then the other spheres are all one-dimensional of some positive radius. And so the orbits in this example are classified by the non-negative reals. For every non-negative real, you get one orbit, and looks something like that. So the observation due in kind of independent context to a few people that kind of ties orbits in with what we're going to talk about is the following. You have a Lie algebra structure on the Lie algebra of a Lie group, which is some kind of alternating gadget satisfying some axioms. And this turns out to canonically give rise to a symplectic structure on the orbit. So a symplectic structure is, again, an alternating gadget on the orbit. The assumptions on the two turn out to match up. And in particular, you can always define a canonical volume form on any such orbit. So there's a canonical notion of the size of an open subset of any such orbit. We'll come back to that in an example. And we'll call that volume form omega. So the orbit method itself, one can think of as a heuristic backed by theorems in some cases, based on an approximate bijection between, on the one hand, so the left-hand side I've called Ir of G. This means irreducible representations in a suitable category. So if G is compact, maybe this means finite dimensional complex representations. In other cases, it might be worth taking the class of, say, tempered irreducible unitary representations. But since it's a heuristic principle, we don't have to define what we mean exactly. So that's the left-hand side. The right-hand side is the set of orbits, the set of cogent orbits for the group. And we'll call the bijection, whenever we have it, at least in some approximate form, pi corresponding to O pi for orbit of pi. And of course, this shouldn't just be a random bijection resulting from some coincidence of cardinalities between the two sets. It should satisfy some compatibility with the natural operations on both sides. So for instance, the natural operations on representations include things like tensor products, induction, restriction, forming Hom spaces, that sort of stuff. So those should all have natural analogs on the other side in terms of the orbits. So the most important compatibility condition that the correspondence specifies is that the orbit should describe the character of the representation. So the character is a function on the group describing the trace of the action of that group element on the representation. And near the identity in the group, we can write elements as exponentials of small elements of the Lie algebra. And the compatibility condition says that on such elements, we can write the character in a fairly explicit form in terms of the orbit. So I'll break this formula down factor by factor. This first factor here, for some purposes, is the most important, but for our purposes will be the least important. So for analytic number theory purposes, it's a Jacobian factor that takes the value 1 at the origin, describing kind of the extent to which the exponential map fails to preserve measure as you move away from the origin, comparing two Haar measures. So this factor we can basically ignore for the rest of the talk. I've written it there now just because it's simpler to write it and forget it than to promise that it's unimportant. The second factor is the more interesting one. It's for us, it's the one that depends upon the orbit. So it's basically the Fourier transform. I mean, it's quite literally the Fourier transform of the symplectic measure on the orbit that we described on the last slide. So we integrate over a Fourier variable xi in the orbit, weighted by the symplectic measure, and we take the Fourier phases attached to each such element. This then defines a function on the Lie algebra of our group, which this identity here says describes the character of the corresponding representation. Okay, so when an identity holds of this shape, it's called the Kirillov formula. It's named after Kirillov, who first proved such identities. I guess he showed that, in fact, this principle, this heuristic orbit method, holds perfectly for nilpotent groups, provided that they're connected, simply connected. In particular, the character formula holds in this form. And it's also been proved, for example, for reductive groups and tempered representations in kind of successive work by many authors. that'll be the case maybe of most interest to us. And one thing that's worth noting, just, if you're staring at a formula like this for the first time, is what it says when x is 0. So when you zoom in near the origin in your Lie algebra, or equivalently near the identity in your Lie group. So there, the left-hand side is the trace of the identity operator on your representation, which we know is the same as the dimension of the representation. So that's what this first identity expresses. And the second identity is what we get by evaluating the right-hand side of the formula when x is 0. So the Jacobian factor is normalized to evaluate to the identity, while the Fourier integral evaluates to the volume of the orbit. So in particular, say for a finite dimensional representation, maybe of a compact group, there's an identity between the dimension of the representation, which will be some finite number, and the cardinality, or sorry, the volume of the orbit with respect to the canonical symplectic measure. Okay, so one example, just to kind of make things very concrete. If the group is SO3, then the representations can be classified by non-negative integers that describe their highest weights. And the precise mechanism for this classification won't matter for us, but we have some labeling of all of the representations by the non-negative integers 0, 1, 2, 3, and so on. So with that labeling, the representation that we get will have dimension 2t plus 1. And it turns out that the Kirillov formula will hold if we take OPi to be the sphere of radius 1/2 more than the highest weight occurring in that label. And so you can see from this, from comparing these two formulas, that it's not quite the spherical volume measure in the usual sense that one takes for d omega. It's something that grows a bit slower than that as the radius increases. But in any event, it is the rotation invariant measure with this total volume. Okay, another thing you can see from this example is that we advertise this method as at least an approximate bijection between representations and orbits. So you can see here that on the one hand, the representations are classified by a non-negative integer. On the other hand, we noted that the orbits are classified by a non-negative real. So of course, these two sets, depending upon which field of mathematics you spend the most time in, either look very, very different or very similar. So for us, we're coming from an analytic number theory perspective where the integers and the reals basically look the same after you zoom out and blur your vision sufficiently. If you average enough, these two sets look quite similar. So for our purposes, this is quite close to a bijection. Once you do enough averaging, it really behaves like a bijection. And I thought, just to conclude this short section, I would give one other quick example kind of relevant for classical modular forms. So if your group is the group PGL2R, which you can think of also as SO12, you can think of elements of its Lie algebra or of the dual Lie algebra as traceless 2x2 matrices with coordinates like this. There are now two classes of orbits. So they're the 1 and 2 sheeted hyperboloids I've indicated here, described by these equations. There are also two classes of irreducible tempered representations, the principal series and the discrete series, and they match up quite nicely with the orbits. Again, you can see that the matching up is not quite bijective. You for example, lose this epsilon, this sign, as you pass from a principal series representation to its orbit. And also, you don't get all of the orbits that arise from the discrete series. You only get the integral ones. But modulo that, it's again quite close to a bijection. So something that I don't think has been done so much, but could be done more, is to try to understand a lot of the special function asymptotics that show up when you work with GL2 analytic number theory and automorphic forms, so Bessel functions, Bessel kernels, and so on, in terms of pictures like this. So this can certainly be done, and it's kind of the theme for what we'll do in the remainder of the talk, although in a slightly different setting. All right, so that's all I wanted to say about the orbit method in general. I don't know if there are any questions about that. But if not, we will continue.
Hi, can I just ask a quick question?
Yeah, sure.
You mentioned before, you explained, and I didn't quite understand, an approximate bijection. In what sense is the bijection approximate?
So it's approximate, for example, because the non-negative integers are not quite in bijection with the non-negative reals.
That's what you meant. Okay.
Yeah.
So I see. Okay.
And so it's neither injective nor surjective. You also lose this epsilon as you go from the representation to the orbit. But, you know, for analytic number theory standards, this is kind of a bijection. It's more or less, you know, when you're averaging over a bunch of things like this, it feels like a bijection. You don't lose too much. Yeah.
Thank you.
Sure. Okay. So let's say a little bit about what we mean by microlocal analysis in the setting of Lie group representations. So microlocal analysis on Rn is, well, if we can devote 6 lines to it, maybe we can summarize it as follows. It's, I guess you could say, the art of taking a function on Rn, maybe an arbitrary function, and trying to understand it in terms of pieces that are localized, hence maybe simpler. By localized, we mean in both the positional sense and the frequency sense. So an example of a function that I think is manifestly localized is a modulated Gaussian. So I've tried to define here a Gaussian as a function of the variable x that's translated by the positional parameter x0 and then modulated by the frequency parameter x0. So the pair x0, x0 will be a 2n tuple of real numbers that maybe most canonically is thought of as living in the cotangent space of Rn. So this Gaussian, because of the term here, will decay rapidly away from x0. And on the other hand, the Fourier transform of this Gaussian will have a very similar form, but with the roles of x0 and x0 swapped, maybe some additional sign thrown in. So the Fourier transform will likewise concentrate quite close to x0. So even though, you know, we know from basic analysis that you can't find a function that, say, is both compactly supported together with its Fourier transform, a function like this kind of splits the difference to the greatest extent possible in the sense that it's concentrated and its Fourier transform is concentrated in rather short intervals, even if they're not literally supported in such short intervals. And typically the way that one decomposes such functions or decomposes functions into pieces like this is through a calculus of operators that behaves as if it projected onto families of functions that were localized kind of in this sense here. So the assignment that generates such operators is typically called op. Yeah, if there's a question, I can understand it. It came through kind of jarbled. And yeah, the assignment op takes as input a symbol, which is some function satisfying some derivative conditions. Maybe the definition depends upon your precise application, and gives rise to some operator on some space, maybe a Hilbert space, such as L2 of your manifold, or maybe a Sobolev space or something else. And well, whatever the definition is, the key characterizing property should be that at least approximately such operators should be diagonalized by the localized functions with an eigenvalue described by the value that the symbol takes at the parameter that you localize at. So on a modulated Gaussian like this, op of A applied to it should give back basically something of similar shape, at least the leading order, times the value of your symbol at the parameter that you're localized at. So we'll be talking about, well, I guess actually a generalization of this story where, you know, implicit in the construction of the pseudodifferential calculus is the Heisenberg group on Rn, which is the group generated by translations and modulations of functions on Rn. And if you pass from the Heisenberg group to a general Lie group, and you kind of replace what you should with what you should, you get another notion of microlocal analysis where rather than decomposing functions into pieces that are localized in the above sense, you're instead decomposing vectors into pieces that are localized in the sense that under small group elements, they behave like approximate eigenvectors. That's the basic idea. And we'll say a bit more precisely what we mean by that in the next couple of slides. So the analogs of the operators that we'll work with in this group theoretic setting are just the integral operators attached to test functions on our group supported near the identity element. So if f is a function supported near the identity in G, we can integrate out the action of f to get an operator on the representation. Now, to work with these meaningfully, we need some way to perhaps parameterize the functions f that we care about. And it turns out that a very convenient way to do that is in terms of their Fourier transforms. Now, what do we mean by Fourier transform? Well, the group G isn't quite abelian, but we're only looking at functions that are supported near the identity. So if we take such a function, we can pull it back to the Lie algebra, where it'll give a function that's now supported near the origin of the Lie algebra. And then we can take the usual Fourier transform of that. And this function on the dual Lie algebra that we get by successively restricting and then taking a Fourier transform, we'll denote by the symbol A. And whenever A and F have this kind of relationship, we'll write op of A for the integral operator attached to the function f. So we'll come back to this so many times, it's maybe worth repeating the definition again. So if you have a nice enough, let's say if you have a Schwartz function on the dual Lie algebra, you can take its Fourier transform. That gives you a test function near the origin of the Lie algebra of the group. And then you can push it forward under the exponential map to give a test function on the group, which you can finally integrate out against the action to define an operator. That story just then is what op of A will refer to. And maybe it's worth just noting that, as one piece of evidence that this is a reasonable way to parameterize our functions, the Kirillov formula for the trace of the action of such operators is described quite simply. So up to this Jacobian factor that I've promised is not so important, it's given just by integrating the symbol A over the coadjuvant orbit against the symplectic volume form. So, other analogies, I guess you could say that OPI plays the role of the phase space in classical pseudo-differential analysis. It's quite literally the analog of the cotangent space to your manifold. And yeah, I think that's all I want to remark about that for now. So these are the operators we'll work with. How about the vectors? So I think the best way to motivate how we think about localized vectors is through the following heuristic. So we might remember that we noted that at least in a finite dimensional setting, the volume of the orbit always matches up with the dimension of the representation. So it's very natural to ask if you can refine this identity, which you can think of as an identity between cardinalities of sets. So on the one hand, the dimension of the representation is the cardinality of a basis for the representation, whereas the volume of the orbit is, well, you can think of it as, say, the number of volume 1 partition elements that you need to cover the orbit. So what we'll describe in this slide amounts to just refining that identity between cardinalities to an actual bijection under some nice enough conditions. So the heuristic says that if we have a partition of the orbit into pieces that are concentrated, each of volume 1, near some specific element of the orbit, so I'll call those pieces p tau, then such a partition should correspond, again, kind of heuristically, to an orthonormal basis for the representation. So I've called the basis elements v tau. So v tau is a vector that matches up with a partition element p tau. And again, it shouldn't be just a completely random bijection. It should be compatible with, for example, the operators we've defined. And the compatibility condition is that, well, what can you do to the vector? You can act on it by the operator. On the other hand, given a symbol, you can evaluate it at the point tau that's kind of a base point of this partition element. And then the compatibility condition is that the operator should act on the localized vector as more or less as if it were an eigenfunction with eigenvalue described by the value of the symbol at that base point. Now, of course, I said base point, reflecting that we had some freedom in choosing tau. So, we could have really chosen any element in this partition element p tau to be our base point tau. And so at the very least, we should ask that the symbols are essentially constant on these partition elements. But maybe assuming that condition, say for the sake of making the right-hand side well-defined, it's not so unreasonable to postulate that such a relation should hold. And just as a matter of terminology, we'll then say that the vector is localized at the point tau, and we'll call the partition element p tau its microlocal support. This is all kind of standard terminology in classical pseudodifferential operators that we're just translating to the situation here. Okay, so an example to give us something to stare at. So let's go back to SO3. Let's let pi be the representation of highest weight t as before. And let's take the partition element. Well, we know that it needs to have volume 1, and it turns out the right size of such a partition element for it to have that volume is roughly t to the half. So meaning each of these triangles is supposed to be something like one of these p taus, and provided that these triangles have diameter or radius roughly t to the half, their volumes will grow like roughly 1. Keeping in mind here that this is the sphere of radius t, and that we're using the normalized symplectic volume form on that sphere. So you can convince yourself that the number of partition elements is then roughly the dimension of the representation. So, the scale kind of matches up. And you can also write down what kind of condition on the function, on the symbol A, is necessary for it to vary mildly on each of these partition elements. So I've written that down here. So if we ask that A behaves like a bump function with derivatives growing a bit slower than t to the epsilon in a rescaled sense, the relevant way to summarize that is that the alpha partial derivative of A should grow like the order of alpha, t to the negative 1/2 minus epsilon, as I've indicated here, raised to that power. So, for example, thinking about first derivatives, this says roughly that A varies by at most t to the negative 1/2 minus epsilon times L over any interval of length L. And if you take L to be the radius of these partition elements, then L times that gives you roughly t to the negative epsilon. So it kind of matches up. Okay, so everything I've said so far has been just kind of hand-wavy, heuristic-y. On the next slide, I'll try to state an honest, at least summary of a theorem where the basic principle is that, so I'll go through this theorem step by step. Each assertion we should think of as kind of an obvious consequence of the heuristic, but the theorem has the benefit of being true and provable in some rigorous sense. So one can, write a paper having the heuristic in mind and just drawing these pictures and being hand wavy. And then when you have to write the paper, you just fill in the details using whatever is actually written here. So, okay, going through the theorem. Yeah, we'll take a unitary representation of a Lie group that depends on some parameter that I've called t. And the dependence is arbitrary. So no restrictions at all. Then the assignment that we've defined above that attaches to a symbol A, say a Schwartz function, an operator op of A, provided that we restrict it to functions that I'll call AT that satisfy the same estimates as on the previous slide, and I've repeated them here for convenience, should enjoy some kind of reasonable microlocal calculus. Meaning these operators should behave as if the heuristics on the previous slides were true. So for example, this first item here says that let's say A is supported on elements of size roughly t and varies in the manner that we motivated on the last slide, then op of A should have operator norm roughly big O of 1. And the heuristic said that op of A should behave like a diagonal matrix diagonalized by these localized vectors with eigenvalues given by the values of the symbol A at these points tau. And of course, a diagonal matrix, all of whose entries are of size big O of 1, should have operator norm big O of 1. So, maybe this isn't, this should be considered an obvious consequence of the heuristic, but again, it has the benefit of being true and usable in argument. So this is a standard tool in harmonic analysis called the Calderon, actually, is it Vaillancourt theorem? I don't know how that's pronounced. Well, anyway, so it's an analog of that theorem. And then, for example, item 2 here says that the trace norms of these operators grow as fast as you'd expect them to based on counting how many partition elements show up in the support of your symbol. The next identity is a composition formula that I just stated in a very abbreviated form. You can think of it at first glance as saying that if op of A and op of B are both approximately diagonal matrices, then their composition should behave like as if it were just what you'd get by multiplying the two symbols pointwise. And then finally, we have similar results for more general symbols, so not just compactly supported things. So for example, for polynomials, so this phrase here I should mention is the reason that there are 2 papers appearing in the theorem attribution. So the second condition is, it's the observation that you don't need so much regularity in directions transverse to the cogent orbits for this calculus to make sense. And I'll just explain what that means in this example. So the only conditions we required in order to ensure that the function A varies mildly on each partition element concerned the variation of that symbol A within the sphere. Whereas if you imagine that the symbol A varied quite a bit as you vary the radius, that would have no bearing whatsoever on this condition. So by direction transverse to the cogent orbits, I mean in this example, a radial direction. And so what this condition here is saying is that we don't need very much regularity in the radial directions. We need just the right amount of regularity in the transversal directions, or sorry, I guess the tangential directions. And yeah, so that's the best summary I could give of this in kind of a slide. I don't know if there are any questions on this. This is all I wanted to say for this section of the talk. And then we'll go into some applications, but yeah. Anything so far?
Hi, Paul, could you maybe say a little bit more about 4, the functions with less regularity, more precisely?
Yeah, sure. So if we go back to this slide, imagine that your function is expressed in polar coordinates as a function of both the radius and kind of some position on the sphere. You can express that your function varies mildly on each of these partition elements entirely in terms of derivatives with respect to the spherical argument, or the radial parameter, I guess you could say. This condition that I've written down here also stipulates some bounds on the radial derivatives, and the content of 4 is that you don't actually need such bounds. So what it allows you to do is it allows you to construct projectors that concentrate on, well, in symbol space, fewer orbits, and in terms of representations, they'll project onto a smaller family of representations. They'll essentially project onto one representation. That's the informal content.
Thanks.
Sure. Okay, so I'll say a few words about applications of these kinds of things. So starting with some of the local applications. So let's take for G and H one of the following pairs of groups. So for instance, GLN plus 1 of R or GLN of R. You can take these other examples as well if you'd like. And basically, I'd suggest taking the example that makes whatever thing we're staring at simplest to think about, because all the examples will behave similarly. So it might be nice, for instance, to take a pair of compact groups. So you could take SON plus 1 and SON. That'd be a good example. So then I guess the distinguishing feature of these pairs of groups is that they are strong Gelfand pairs, which says something about the multiplicity of restrictions of irreducible representations from the bigger group down to the smaller group. So in the case of a compact pair of groups, this is very easy to understand. It just says that if you take an irreducible representation of G and you restrict it to H, it decomposes as a direct sum of irreducibles where each summand occurs at most once. Now, in the more general setting, the right way to formulate this is as a direct integral decomposition, where the way you formulate that is you say that the norms of vectors in the representation you start with can be computed by integrating norms of certain projections of that vector to representations of the smaller group. So in the setting again of a compact pair of groups, these would just be like you take your vector, you decompose it under the action of the smaller group, and then you can consider the projection onto each summand in that decomposition. And of course, the norms will add up after squaring to the norm of the vector you started with. This is a more general form of that where you have to weight it by an integral. And of course, when one defines direct integral decompositions, there's always this issue of choosing a measure within a measure class. So you can always multiply your measure by any invertible measurable function. And the way we can normalize it, it turns out in these examples, is by taking that measure to be the Plancherel measure on the dual of our group. Okay, so we'll talk about a couple problems concerning such decompositions of representations.
Well, there is a question in the chat.
Oh, yeah,
I don't know
sure.
if you can read this.
No, I have not, or I did not have it visible. There it is. Okay. Do we need pi to be tempered? Yeah, it is tempered. Yeah. Oh, okay. You asked, do we need it to be tempered? So we don't need it to be tempered for multiplicity 1 to hold, but we do need it to be tempered for what we're going to talk about to make sense. So we'll want these projections to be defined and normalized in certain ways that would not be available otherwise. Okay. Oh, and also, I guess if pi is not tempered, then what I wrote here is not true, because this we would not be able to take this measure to be the Plancherel measure in general. So if, for example, if pi is trivial, then its restriction will be trivial, and will, at least if G and H are not compact, it'll not be in the support of the Plancherel measure. Okay, so here are a couple problems that we'll address partially, and I think there are many interesting further questions about such problems, but we'll see what we have. So first of all, we'll consider a family of irreducible representations of the group H. So of course, it's technical to say what we really mean by this, but I guess, you know, when you classify the irreducibles, you classify them in terms of some parameters. So maybe by a family, we mean a set obtained by putting some conditions on those parameters. So maybe asking that they belong in some interval or product of intervals of some reasonable size. So problem 1, can we construct a vector in the representation pi of the bigger group G that picks off our family? In the following sense, when we compute the projection of the vector onto some irreducible representation of the smaller group, this should be roughly 1 if that representation lies in our family and 0 otherwise. So in other words, the projections of our vector to representations thought of as a function on the set of such representations should pick off the characteristic function of our family. That's kind of the idea. And to make the problem a little more, well, maybe meaningful and also challenging, we would like to be able to do something with the vector that we produce. So we're not looking for a kind of soft functional analytic argument that produces an abstract vector. We'd like a vector that we can, for instance, estimate the matrix coefficient of under the bigger group G. I mean, I guess you can imagine a functional analytic argument giving such a vector, but perhaps only specifying how it transforms under the smaller group H. So problem 2 is kind of the way we'll end up addressing problem 1. So let's assume, we'll go back to the heuristic language because it makes the statement more intelligible. We'll assume we have a localized basis of a representation. So pi given has the basis v tau, where v tau corresponds to some partition element p tau of our cogent orbit. And the question we'll ask then is, can we then work out the asymptotic behavior of the projections of these localized vectors to any given irreducible representation of the group H? And you can imagine that if you can answer this second question convincingly enough, it gives a reasonable tool for constructing an answer to the first question, because you could try, constructing your vector v in terms of localized vectors, and then using that to produce a vector or maybe family of vectors that cuts off your family. So really problem 2 will be what we'll actually address, but in our applications, problem 1 is the motivation for doing so. Now, both these problems are, of course, problems about the representation theory of the groups G and H. And, we're giving a talk about applications of the orbit method to analysis of representations. So perhaps unsurprisingly, we can translate these problems into some analogous problems formulated in terms of the orbits. So on the next slide, we'll say what those problems are. So rather than starting with a representation pi and restricting it to H and then decomposing that, I guess the analogous operation at the level of cogent orbits is you take the orbits and you intersect them after pulling the orbit of the smaller group up to the dually algebra of the bigger group. And we'll call that intersection, I mean, maybe one could call that a relative cogent orbit. That's probably not great terminology because it's not always literally an orbit, but well, we'll write O pi sigma for that intersection. And skipping ahead a bit, I've drawn some pictures of what these O pi sigmas look like in examples down here. So say for SO3 and SO2, we know that O pi maybe looks like the sphere. Whereas O sigma, so sigma for SO2, its cogent orbit will just be a point describing the frequency that sigma rotates at. And so the preimage of a point under a projection from R3 to that point inside a sphere will be one of these little equatorial strips going around the sphere. Those are what I've tried to draw in this picture on the left. So the equator and every other strip parallel to it is an example of an O pi sigma. I've drawn some other examples for the group PGL2R on the right-hand side here. So all of these hyperboloids, all these conic sections, as well as this cross, these are examples of O pi sigmas. Now there's an important condition on pi and sigma, which is that, so we call pi and sigma stable if the set O pi sigma, which I guess in general is a set that the group H acts on, if the action of that group equips that set with the structure of a torsor, meaning if we have a closed orbit and a trivial stabilizer, then we'll say that the pair pi and sigma is stable. And this turns out to match up with the standard terminology from geometric theory for the stability of the action of a reductive group on an affine variety. It's just the specialization of that to this group H, and the affine variety is the dually algebra of G. Now, I mean, you can see in this example that, for instance, H is SO2, and H, as you can imagine, acts on each of these equatorial strips simply transitively. You can kind of see that from the picture. And also GL1R will act simply transitively on each of these hyperbolas. So in these pictures, most of the orbits that I've drawn are stable. It's only when you get kind of close to the north or south poles of the sphere, or very close to this cross, that the condition starts to break down. And so as I've indicated here, yeah, this is a generic condition. in several senses. It turns out to depend only on the infinitesimal characters of the representations. So more informally, so these infinitesimal characters can be described in terms of eigenvalues attached to standard representations. And the condition turns out to be equivalent to these eigenvalue sets not overlapping at all. So here, for SO3, I guess the eigenvalue set for the representation of the big group SO3 consists of t and negative t up to plus or minus a half or so. And so you can see that it's when the vertical parameter describing sigma tends to t that stability breaks down, or when it tends to negative t. So anytime you approach an overlap condition, the stability breaks down. Okay, and on the next slide, I'll refer informally to some pairs pi and sigma being uniformly stable, which means that this condition should hold with a bit of room. So the picture should stay uniformly away from the north and south poles on the left and uniformly away from the cross on the right. Or more rigorously, the condition I've written down here should kind of hold, there should be a compact set on which it holds that all of our pairs belong to. That's what that'll mean. Okay, so an informal statement of the theorem we get is that if we take any sequence indexed by a parameter t of tempered representations satisfying this uniform stability condition, which means rigorously that the rescaled pair of infinitesimal characters lies in some fixed compact collection satisfying the stability condition, then we can compute the norms of the projections of localized vectors in terms of what we might expect from the orbit method, which is that they're asymptotic to the volumes of these sets O pi sigma intersect the microlocal supports of the vectors. Where here by volume, we mean what we get by taking the Haar measure on H and transporting it to the torsor O pi sigma. So the distinguishing feature of these stable pairs is that we actually have a torsor, and so we can define the right-hand side. And so assuming the right-hand side can be defined, we'll prove this informally stated theorem saying that the sizes of these projections are given roughly by volumes. So maybe imagine that p tau is something like a little blob, one of these triangles. And what it's saying here is that to compute the size of the projection of the corresponding vector to sigma, what you do is you compute the overlap between O pi sigma and your blob.
And this is what you meant by theorem 2. You listed 2 theorems and you were going to prove the second one. Is this basically the incarnation of theorem 2?
Did I mention theorem 2? I don't remember that.
You gave one. The first one was like control the matrix coefficients, and you said that.
Oh, sorry. Yeah, I mentioned problem 2. This addresses
okay.
This addresses problem 2. That's right.
Yeah.
Yes.
Okay.
Yep. And I put on the next slide, if anyone's curious, like an actual precise statement, because this statement, of course, involves these localized vectors v tau. And the actual precise statement is what you get by kind of averaging that over a very small family of parameters tau. And the way you do that is you take a function a on the dual Lie algebra, you construct op of a, which we should think of as a proxy for these localized vectors v tau, provided that the support of a is chosen close enough to tau. And then, yeah, you define this relative character that I've indicated here, which is, I guess we should think of it as, it's the bilinearization of the quadratic form or Hermitian form that assigns to each vector the size of its projection onto the representation of sigma. And then the precise statement is that this sum here that I've called h pi sigma of a is asymptotic to the integral of the symbol over O pi sigma, which recovers the informal case I tried to describe on the previous slide. If you take a to be something like the characteristic function of one of these partition elements. Okay. So I guess I'll just very briefly indicate a couple of global applications. I didn't plan to talk much about the details there, but yeah, we apply these techniques to automorphic forms in the setting of a pair of groups G and H is above, something like GLN+1 and GLN. We'll have a pair of arithmetic lattices that I'll call gamma and gamma H, something like GLN+1 of Z and GLN of Z, although we'll stick to compact examples for now. We'll have the corresponding quotients that I'll call brackets G and brackets H, which are now the spaces in which our automorphic forms will live. And we'll have a pair of automorphic representations that I'll call pi and sigma. So pi for G and sigma for H. So these are spaces of functions on these quotients that I guess we should informally think of as being like all of the functions that satisfy some family of differential equations. That's kind of the basic content. And now, I guess I promised that the talk would be about applications to L functions. And the connection to L functions comes from a conjecture that's actually a theorem in some cases. So it's called the refined Gongorus-Prasad conjecture. There's a lot of work on it that I've tried to mention some names about at the bottom here, which says that integrals of automorphic forms are related to special values of L functions where the proportionality constants in the relation are these relative characters we studied in the previous section, describing the projections of vectors onto representations of smaller groups. So, we don't have time to talk about anything meaningful about what L functions are or whatever, but this is an identity that connects them to integrals of automorphic forms on the one hand, and to special functions from representation theory on the other hand. And so just to give an informal summary of results, we'll consider something like a pair of automorphic representations, pi and sigma, of GLN+1 and GLN. The important thing to know is that they're labeled by a pair of, or by, I guess, a tuple of parameters. So the number of parameters is the index of the group. So say T1 through Tn+1 for GLN+1. We can form a tensor product parameter, which will then have parameters given by the pairwise sums of the two collections of parameters. And to state our results rigorously, we should really replace the general linear groups by a pair of anisotropic unitary groups so that everything lives in a compact quotient. And then assuming these conditions, we get some theorems that say, in some cases that we can estimate averages of L functions over either varying the automorphic form on either group in some new cases, both individually and on average. So the first result concerns dyadic families where we vary the automorphic form on the smaller group. And the second result concerns somewhat more sharply concentrated families where we vary the automorphic form on the bigger group. And in particular, if we constrain the parameters of the product to all be of roughly the same size, then we can prove a non-trivial estimate with a power savings, very small power, but positive for the L value. And so I can just say that the proofs combine, well, the relative character asymptotics that we talked about earlier with some additional global input coming in the first theorem from ergodic theory, and then the second input from some analysis of a relative trace formula. And yeah, I think I will not, I have some bonus slides where I kind of maybe just summarize some ideas from that proof. So, we'll choose our symbol kind of like this to concentrate very close to one of these orbits. We'll then write down the relative trace formula that we get from the corresponding test function. We'll analyze the whole thing. It turns out the main point will be to show that the gamma not in H contribute a smaller order to the right-hand side. And when you stare at that problem for the specific choice of F that we have, it ends up boiling down to exhibiting transversality between a certain pair of subvarieties inside your coadjuvant orbit. So kind of all of the analysis is bundled up with thinking about these orbits, even on the geometric side when we're trying to, bound things over there. I'd be happy to kind of more patiently go through what exactly this problem is, if anyone has questions. But I thought I'd conclude with just saying, what is the actual theorem in linear algebra that everything boils down to once you've, used kind of a spectral analysis, and then a relative trace formula, and then a bit of multivariable calculus to reduce things to the Lie algebra. And then once you boil everything down to a linear algebra problem, this is what you turn out to get. So it's a kind of pleasant, completely explicit linear algebra fact about solutions of linear equations in terms of commutators of matrices. I don't know how to, I don't have much more to say about that other than that it's an elementary fact that I don't know of a super elementary proof. So maybe if enough of us assign it as a bonus problem for linear algebra exams, someone will come up with a more elementary proof. And I'll conclude just by recording the summary of what we've done. So we've developed the orbit method in some kind of analytic form as a microlocal calculus for Lie group representations, which is sharp in all aspects. So as far as vectors within representations, and as far as families of representations, at least up to epsilons. We use that to do some local analysis of relative character asymptotics subject to this stability condition. And then we applied that together with some additional arguments, global and local, to prove some new estimates for L functions. And with that, I will stop and thank you all for showing up.